All right, let's get started. We're going to talk about set theory for a few days. And if we're going to talk about set theory, we better have an understanding of what a set is. A set is a collection of objects, and we call those objects elements. There are a few special sets that I want to discuss with you, very important for elementary school for sure. The first of those are the natural numbers. And we abbreviate the natural numbers with a boldface N. I can't really write a boldface N, so the way that I'll do that is like this. There's a boldface N to represent the natural numbers. And what the natural numbers are the numbers that they occur in nature. We can count them. That's 1, 2, 3, and that keeps going forever. Something really important I want you to notice about how I've written that set down, the natural numbers, is I've listed out all the elements. That's called roster form. We've listed out all the elements in a roster. And when we write a set this way, in roster form, we use braces on the ends. So we use braces on the left and right to frame our elements. We do not use parentheses. We do not use braces. We do not use parentheses. We do not use brackets. We use braces whenever we're going to write a set in roster form. If you're typing it, this is on your keyboard to the right of the P, you'll see brackets on the bottom and braces on the top, and that's what we're going to use to write a set in roster form. We're going to use braces. So that's going to be important to distinguish the fact that what we have is a set written in roster form, is those braces. All right, let's look at a couple other important sets for us. Let me make some space here real quick. Okay. So another important set for us, in addition to the natural numbers, are the whole numbers. And we're going to use a boldface W. That's not the easiest thing in the world to do. I'll do that. There's a boldface W. And the whole numbers are really just the natural numbers with 0 thrown in. So that's 0, 1, 2, 3. And that keeps going on forever. And we use braces to write that set in roster form. If when I say braces to write that set in roster form, if you're not sure what that means, it's okay to ask about it. And then finally, the third set that we're going to look at are the integers. You might think a bold-faced I for integers, but any of you who've taken maybe Algebra 2 or pre-calculus know that I is sort of tied to imaginary numbers, so I has a whole separate meaning. So instead, for integers, we're going to use a bold-faced Z. That's our abbreviation for integers. And integers are the whole numbers and their opposites. Opposites would be the negatives. So this goes on to negative infinity, and it's -2, -1, 0, 1, 2, and it goes on forever to positive infinity. And so that's our integers. Not sure exactly why it's Z. I'm thinking we're not going to use I because that has a different meaning. So let's just use something totally different. We'll go with Z, and that's integers. So natural numbers, whole numbers, and integers are those three sets. We won't talk about those a ton, but I do want you to be comfortable with what are the natural numbers, what are the whole numbers, what are the integers. Objects within a set. There's a symbol for element. We said that the objects inside a set are called elements, and we have a symbol for that. This symbol right here means is an element of. So that E looking symbol means is an element of. Examples of that, the way that that's used, would be 1 is an element of 1, 2, 3. That would be a true statement. This element is a member of this set over here. And then very much like equal to and not equal to, this symbol means is not an element of. And as you can see right here, 5 is not an element of the set 1, 2, 3. It's not in there, so it's not an element. So is an element, is not an element. Those are symbols that may be new for you. I don't think they'll give you much trouble. It's just important to know what that symbol means. One thing I want to point out here for sure is that 3 written inside braces is a set because the braces make it a set. It's not a very large set. It only has one element, just that 3, that's it. But as long as it has those braces around it, it's a set. If we instead write it without any braces, now it's just something that could be an element of a set. You'll notice this 1 is an element of 1, 2, 3. No braces around that 1. So this thing could be an element of this. This 5 could be an element of this set. Turned out it wasn't, but that's an important distinction for you to be aware of. Braces make something a set. If it doesn't have the braces, then it's just an element. Something that could cause a little confusion is down at the bottom there, R, and the set RSTV, and whether or not it would be an element. This is a capital R, this is a lowercase r. Those are different from each other. And Laura may be ahead of me here. I'll give her a chance. But that we would say then that capital R and that lowercase r, we have to make a decision on whether or not those are the same as each other. Would the capital R be an element of that set? Is it or not? That's a question we'd have to answer. And the answer is no, it's not an element. The capital R is different from the lowercase r, so that capital R is not an element of the set RSTV. As you'll see later today, it'll be real common for us to use capital letters as the name of a set rather than being inside the set. That's sort of a custom that we'll do. As we go through these things, make sure you let me know if you have questions. This is kind of just definition stuff that we'll go through before we start asking and answering any questions. Oops. Equivalent and equal. 2 more definitions for us. Equivalent. Our symbol for equivalent is a tilde. It's at the very top left of your keyboard there, next to the number 1. That's a tilde, and mathematically that means equivalent. The definition of equivalent is that the sets have the same number of elements. So 2 sets are considered to be equivalent if they have the same number of elements. So I look here, and this set on the left, 5 and 8, that has 2 elements. And this set on the right, EK, it has 2 elements. Since they have the same number of elements, we say yes, they are equivalent. If 2 sets have the same number of elements, they are equivalent. If we say they're equivalent, then you know they have the same number of elements. Again, let me know if any questions come up as we talk through these things. Our next definition down here is equal. Same symbol for equal that you've always known. If 2 sets are equal, they have the exact same elements. And so here we look and we have 7, 12, 19. Over there we have 12, 7, 9. They're in a different order. Does that matter? No, that doesn't matter. The order that they're written in makes no difference at all. It's going to be customary for us to write them from least to greatest, like the one on the left, but you don't have to. The elements within a set can be written in any order, it doesn't matter. And so here I have 7, 12, 19. Here I have 7, 12, 19. Those 2 sets have the exact same elements, so we would say that they are equal. Let me know if you have any questions on that before I take an opportunity to ask you a couple of questions. Okay. Couple of true false. I'll make a poll for this and give you an opportunity to tell me true or false. false questions kind of feels like, wow, it's true or false. How hard could it be? They're not always easy. So let's see how this one turns out. The first one is true or false. Those two sets are equal. The bottom one is true or false. Those two sets are equivalent. This is just leaning into what the definition of equivalent is and the definition of equal is. That's what these questions are about. We'll go 20 more seconds, and then we'll talk through it. All right, let's see how we did here. Okay, strong agreement, not unanimous, and spread over every one of the possible results. That's kind of an interesting outcome here. All right, so let's take a look at these. First, let's remember what equivalent and equal mean. If two sets are equivalent, then they have the same number of elements. If two sets are equal, then they have the exact same elements. So let's take a look. True or false? The first one says 369 is equal to 693. Well, 369, this is 369. The order doesn't matter. You can change the order around. It's still the same elements that are inside those two sets. So sure enough, they both contain 3, 6, 9. So those two sets are equal. This would be true. Down at the bottom, this is a borderline trick question. I'll allow you to be a little bit like, really, on this one. But after 1 minute from now, then you're not allowed to think it's a trick question anymore. So here we have DEFG is equivalent to DEFG. Well, what equivalent means is they have the same number of elements. Well, this one has 1, 2, 3, 4 elements, and this one has 1, 2, 3, 4 elements. They both have 4 elements. So are they equivalent to each other? Do they have the same number of elements? They sure do. So that is a true statement. Those two sets are equivalent. You might say, yeah, but these two sets right here are equal. You're right, they are, but that's not what the question was. The question was, is this a true statement? Are those two sets equivalent? And the answer to that is yes, they are. So that's a true statement. You're right, they also happen to be equal. What you might pull from there is that once we know two sets are equal, then they have to be equivalent. Because if they're the exact same elements, then they must have the same number of elements. That would be true. Any questions on what we did there? It's no longer a trick question. Now you know if we have equal sets that they must be equivalent. All right, very good. The empty set. The empty set is a set that contains no elements. And we have two different ways that we can write down the empty set. One way is roster form. We can use braces and list out all the elements and just write it as a set with no elements in it. That's one way. Another way is with this symbol right here. Now that symbol for us is going to be the empty set. You may have seen that symbol before when you were doing algebra, and you might have called that symbol no solution. And that's completely fine, but I want to dive into that a little bit and talk about what was actually happening there. So when we solve an algebra problem, let's say x plus 5 equals 7. And we subtract 5 from both sides and find out that x is 2. And typically for us, or in an algebra class, and you would just say x equals 2 and you would move on. In a more formal setting, What you might be asked to do here is write the solution set for this particular equation. And that solution set would be a set with 2 in it. There's a set that contains all the possible solutions to that equation. We could write it as a set. And then sometimes we're doing math and we haven't learned imaginary numbers yet, and we get to y is equal to the square root of -4. And if you haven't learned imaginary numbers yet, then you would look at that and say, there's no solution. You can't take the square root of a negative, and you just write it like this. What you're really doing is say, if I write down all the possible solutions, there aren't any. And so the solution set is the empty set. Really, anytime that you were doing an algebra problem and you wrote no solution, what you were really saying is the solution set is the empty set. Anyway, for our purposes, the empty set is a set that contains no elements, and you can write it in either of those 2 ways. One distinction I want to make sure to point out is the empty set is not the same as a set that just contains 0. This set right here, it has an element in it. It has 0 in it. So that's not an empty set. This is not an empty set. This is a set that does have an element. That element just happens to be a 0. Any questions on the empty set? Okay. Our next definition topic is subsets. When all the elements of one set are found in another, the first set is a subset of the second. This makes a lot more sense when we put some actual elements and sets together. So I'm going to say the set AB, and I have over here the set ABC. And now we'll read that definition again. When all the elements of one set are found in another, the first set is a subset of the second. So when all of the elements of this set are found in this other set, then we can say that this first set is a subset of the second set. Because basically everything that's in here can be found in that one. So it's a subset. It's came from there. The symbol we're going to use for subset is this right here. It's a lot like the element symbol, but it doesn't have the line in the middle to make it look like an E. And so what we would say is the set AB is a subset of the set ABC. And that would be a true statement. AB is a subset of ABC. In some other books, you may also see this as a symbol for subset. We're not going to talk about the distinction and the difference between these two things. For our purposes, we're going to treat those as the same. We really only spend a small part of one day on subsets. So we're just going to treat those as the same and not worry about distinguishing between the two. I mentioned earlier when we had that capital R and the lowercase r that those are not the same as each other. And this is just a reminder that it's going to be common for us to use capital letters as the names of sets. And you'll see exactly what I mean by that in just a minute. Continuing our discussion of subsets, now we're going to use capital letters to name sets. So I have set A here is 5, 6, 7, 8. Set B is 6, 7. Set C is 3, 5, 7. What this does for me, or you, is it allows you to write down a set without having to list all the elements every time. For example, we can ask the question, is B a subset of A, without having to write all those elements down every single time? Now, that's my question to you. Is B a subset of A? What do you think? And it's just a yes or no, that's all. All right, whole bunch of yeses. Laura, Alondra, Kate, Christopher, Katrina, Joanne, Will, very good. I agree with you. Yes, it's a subset because what we're saying here is 6, 7 is a subset of 5, 6, 7, 8. Everything in B is in A. There's nothing that ruins that. So it's a subset, yes. Let's try the one at the bottom. Is C a subset of A? All right, whole bunch of no's. Very good. We totally get the idea of what makes something a subset. Now, my question is, how do you know? How did you make that decision? What is it that convinced you that C is not a subset of A? And you don't need long flower language here. What made you say no? How did you decide that C is not a subset of A? C has a 3, there's no 3. They don't have to match all the way, Will. That would make them equal. To be a subset, these just have to all be in here. They don't have to match completely. We just have to be able to create B using only what's in A, and it worked in the top one. C does not contain the same elements. Laura wrote the same thing. They don't have to be the same. The same would be equal. It's okay if you aren't equal. You could still be a subset. It's just that everything in B has to be in A for our answer to be yes. Everything in C would have to be in A for it to be a subset. And what you guys are telling me there is that 3 is a problem. We have 3, 5, 7 is a subset of 5, 6, 7, 8. And you know what? The way that I'm going to say no here is because this 3 is a problem. That 3 is a problem. The 3 wrecks it. That 3 makes it so it is not a subset. So we would say no, C is not a subset of A. And it's the 3 that wrecks it. That's the thing that's going to decide for us whether or not something is a subset is there anything in here that wrecks it? That's how I want you to answer a question about is it a subset or not. No. A is 5. No, we wouldn't do that, Stephen, because if we're going to put it, I understand your question now. My first thought was, what? But no, Stephen, we wouldn't write it that way because if we're going to list the elements in roster form, then we're going to list all the elements out. So we wouldn't write it that way because anytime we're going to use braces, we're just going to put elements inside. That's how I want to phrase that. That's a good question, though. When we're deciding whether or not something is a subset, we're deciding, is there anything in there that wrecks it? I want you to keep that in mind as we go on to the next thing. There's sets A, B, and C. And I have a couple of questions for you. And these are going to be yes, no. I'm going to make a poll for this. And they're going to be yes, no questions. So a couple of yes or no questions. Is B a subset of B? Is the empty set a subset of B? Remember what our approach is. Remember what our condition is. How are we going to decide whether or not something is a subset of the other thing? And that's, is there something that wrecks it? We'll go another 20 seconds on this, and then we'll talk through it together. All right, let's see how we did. Okay, there's agreement here, but we're kind of split, and we have all four choices, so that's really interesting. This is one that I tend to expect to go a little sideways. So let's take a look at this together. Keeping in mind the way that we decide whether or not something is a subset is there anything in there that wrecks it? So is B a subset of B? All right, well, let me think about this. Is 6, 7, oops, not parentheses, braces, is that a subset of 6, 7? And the question we ask ourselves to decide is there anything in here that wrecks it from being a subset? Is there anything in here that's not in this one? No, there's nothing that wrecks it. If this were 4, 6, 7, then we would say, no, it's not a subset. But 6, 7, a subset of 6, 7? Sure enough, yes, it is. That was by far the most common answer for that first one. Our gut instinct is to say, no, it can't be a subset of itself. Well, remember, the way we decide whether it's a subset or not is there something that wrecks it? There's nothing that wrecks it, so it's perfectly fine. Yes. What we get from this is every set is a subset of itself. There's nothing that wrecks it. So no matter what the set is, it's a subset of itself. Students usually accept that one pretty easily. This next one, not so much. Is the empty set a subset of B? Is that a subset of set B? And in answering this question, is there anything that wrecks it? A lot of people said no for this. My question to you is, what did you find in here that prevents it from being a subset? What's in there that's not in this one? And I guess the way I'd phrase that, is there anything in here that's not in this? And the absence of 6 and 7, that's not our criteria there, Christopher. We're saying, is there anything that wrecks it? That would make it a subset. Because we don't want to go down that road, because we would agree that 6 is a subset of 6, 7. And you could say, well, the absence of 7. Well, no, that's not how we do this. We look for something that wrecks it. Is there anything that wrecks it? And if there's nothing that wrecks it, then it's okay to be a subset. And when we look at this, there's nothing in here that is not found in the other set. And so what that means is, as hard as this is to want to accept, that the empty set is a subset of B. What this gives us is the conclusion that the empty set is a subset of every set. No matter what your set is, the empty set will be a subset of it, because there is never going to be anything in there that wrecks it, because there's nothing in there. Before we did this, I might call both of these trick questions. Now we know they're not. We've come to the conclusion that every set is a subset of itself. So is B a subset of B? Yes, it is. We've come to the other conclusion that the empty set is a subset of every set. So is the empty set a subset of B? Yes, it is. Because there's nothing that wrecks it. We can discuss that more if you want to. I know it's a tough, especially the one at the bottom, can be a tough one to want to accept. But our criteria is there something that wrecks it? And if there's not something that wrecks it, then we're good. It's a subset. Back here, we said, how come C is not a subset of A? Well, there's a 3 in there that kind of poisons the apple, if you will. But if there's nothing that wrecks it, then it's a subset. All right. Finding subsets. If we're given a set can we find all the subsets of that set? Okay, well, there's our same sets we've been working with, A, B, and C. And our job here is to find all the subsets of B. You might be thinking, boy, that's going to be a lot. How am I going to get them all? You're right. And the way we're going to get them all is we're going to be organized. When I want all the subsets of B, I can see here that B has two elements in it. So if I'm going to list out all the subsets, I'm going to start by listing the sets that have two elements. All the subsets that have two elements. And then I'm also going to make sure I list the subsets that have one element. And then finally, because I just learned that the empty set is a subset of every set, I'm also going to list the subsets that have no elements. And this is how I'm going to find all the subsets of set B up there. So let's see. A subset that has two elements, well, that would have to be this, the whole thing. That's it. Every set is a subset of itself, so I definitely want to count that as one of the subsets. Okay, now the subsets with one element. Well, with one element, I could have a subset that's this, or I could have a subset that's that. And that's all of them. The 6 by itself, the 7 by itself, that's it. And then the subset with no elements, well, that's just the empty set. And so if I wanted to list out all of the subsets of set B, I wind up with 1, 2, 3, 4 of them. There are 4 total subsets of set B because I listed out everything with 2, everything with 1, everything with 0. Can't have a subset with 3 elements because that B doesn't have 3 elements. So there's no way that would work. Let me know if you have questions on this before I have you try one. All right. How many subsets does set C have? I'll make a poll for this one. So here we're trying to find all the subsets of set C and say how many that is. For right now, we do this by listing them out, and that's a great way to do it. As you go through the homework for this section, you might find something else that you like to do also. But for right now, we're just listing them out. We'll go another 20 seconds, and then we'll talk through how many subsets of C there are. All right, let's see what we've got. Okay, agreement, but we're spread around all 4 choices again. That makes things a little interesting. Good, Laura. That's all right. It's good to be challenged every now and again. So let's take a look here and see. The way we want to approach this is we're supposed to find the subsets of C. And so C is this set right here. It has 3 elements. So when I go to list out all the subsets of that set, I want to list out the sets that have 3 elements, the sets that have 2 elements, the sets that have 1 element, and I don't want to forget the set that has no elements because the empty set is a subset of every set. So I know I want to count this empty set here. And when I list these, so 3 elements, that's just 3, 5, 7. That's the only set with 3 elements that would be a subset of C. Now with 2 elements, well, I could put the 3 with the 5. I could put the 3 with the 7. And then I could put the 5 with the 7. This can be a little tricky to miss some. Just try to be as organized as possible. We put the 3 with the 5, we put the 3 with the 7, and then what we haven't done yet is put the 5 with the 7. With 1 element, well, that's not so bad. That's just the 3 by itself, the 5 by itself, and the 7 by itself, and then no elements, empty set. So we've listed them all out, and it looks like we have 1, 2, 3, 4, 5, 6, 7, 8 different subsets of set C. The easiest 2 to miss are every set is a subset of itself, and the empty set is a subset of every set. Make sure you don't miss those 2. Let me know if you have questions on that before we get into some operations with sets. All right, up to now has been a whole bunch of definitions, and we still have definitions coming up, but now we're actually going to solve some problems that involve sets. And the first definition we're going to talk about is the intersection of 2 sets. And when you think intersection, if you were to think about the intersection of 2 roads, the intersection is where those 2 roads overlap. That would be the intersection of those 2 roads. It's where they overlap. When we talk about the intersection of 2 sets, we're talking about where they overlap, what they have in common. The symbol we're going to use to represent intersection looks like this. And it's really easy to remember because if we were going to write the word intersection, it's kind of right in there. And so if we wanted to find A intersect C, and this might be a problem we're asked to do, find A intersect C. Okay, what we're looking for when we're looking for A intersect C, when we're looking for the intersection, we're looking for the overlap, we're looking for the elements they have in common. We're looking for the elements that are in both sets. We're looking for the elements that are in A and they're in C. They have to be in both sets. They have to be what's in common. So A intersect C here is, well, let's see. A is 5, 6, 7, 8. C is 3, 5, 7. What they have in common is the 5 and the 7. So A intersect C is the set 5, 7. Let me know if you have any questions on how we got that. The elements that are in both sets, the elements that are in A and in C are 5, 7. If you wrote it 7, 5, it's not wrong, but our general convention is going to be to go lowest to biggest. So we put 5, 7. All right, I want you to try one. I want you to find B intersect C, and I'm going to make a poll for this. It'll probably take me longer to type the poll than it will for you to answer it. Just hang in there with me. That's funny. That's why I gave you multiple choice, Laura. There you go. So here we're looking for B intersect C. And this is definitely the type of question you can expect to see on that worksheet that's part of the homework and on the quiz and likely on the exam. I don't know if I will, Laura. We may have to wait and see. Let's go another 15 seconds on this, and then we'll talk through it. All right, let's see how we did. Strong agreement here and not spread out all over the place, which is really good. So let's take a look at finding B intersect C. So if we want B intersect C, what we're looking at here is we have set B, which is 6, 7. We have C, which is 3, 5, 7. And we're looking for B intersect C. That's where they overlap, what they have in common, the elements that are in both sets, the elements that are in B and in C. And there's only one of those, it's the 7. That's it. So I might not have answered your question, Laura. I'll give you a chance to throw it out there. The empty set could be relevant here. Let's say we had set D that was 10, 11, 12, 13. And the question said, find B intersect D. Well, now B is 6, 7, D is 10, 11, 12, 13. So their intersection is the empty set. So that's how the empty set could be relevant. Great question. That's a beautiful question. Yeah, sometimes sets don't have anything in common, so their intersection is the empty set. Okay, perfect. Very good. Very good. All right, so that's intersection. Up next, we have union. Union, kind of like a marriage, is when we join sets together. We're going to join two sets together. So now, instead of looking for the elements that are in both sets, we're looking for the elements that are in one or the other. And I say the word or here. If we're looking for, let's say, A union C, if we want A joined with C, we're going to keep all the elements that are in A or in C. And I want to make a quick point about two different types of or here. When you go to a restaurant and the waiter says, would you like soup or salad? What that typically means is you can have soup, you can have salad, but you can't have both. That's exclusive or. If you go to a hot dog vendor and the hot dog vendor says, do you want ketchup or mustard? You could have ketchup, you could have mustard, and you could have both. Both is okay here. Inclusive or is the type of or we use in mathematics. So when we say A union C is the elements that are in A or in C, that means if you're in A, we keep you. If you're in C, we keep you. If you happen to be in both, great. we'll keep you too. So we're keeping all of A, we're keeping all of C. So when we join these sets together, A union C would be this 5, 6, 7, 8 joined with 3, 5, 7. It's not wrong to write it as 5, 6, 7, 8, and then join it with the 3, 5, 7. We don't write them twice. Once they're in there, they're in there. We're not going to write them again. So we're not going to put 5 and 7 in there again. They're already in there. We don't need to write them again. It's not wrong to write it that way, but our convention is going to be to write it least to greatest. So we're going to go 3, 5, 6, 7, 8. It's just easier to look at and make sense of when they're in numerical order. So that's A union C. We've joined those two sets together. It's the elements that are in A or in C. Another way to say this, it's all the elements that are in at least one of those two sets. If you're in at least one of those two sets, you're in the union. If you're in A, good enough. If you're in C, good enough. If you happen to be in both, that's fine. At least one of the two sets means you're good enough to keep. I'm going to have you do a union. I'm going to make a poll for it. I want you to find B union C. Here again, I'll make a poll. Oh, and I didn't tell you that the symbol for union is that U-looking shape, but it is. It's the intersection shape turned upside down to look like a U. That's for union. Really easy to remember. I'll write that down after the poll's done. Here again, probably takes me longer to type this one than it does for you to find the answer, but that's okay. B union C. Intersection and union kind of work in conjunction with each other in set theory. Those are operations we can do. We can find the intersection of sets. We can find the union of sets. We'll go another 15 seconds and then talk through this one. All right, let's see how it went. Almost unanimous, not quite. Very close though. So that's a good thing. And again, not spread out all over the place. So pretty strong response. All right, so B union C here, we want to use, oh yeah, the symbol for union is like that. Easy to remember because it's kind of the first letter of union. So if I want B union C, then what I need to do here is take B and join it with C. And written from least to greatest, that's going to be 3, 5, 6, 7. That was our most common answer by far. If you have any questions, let me know. One thing that you may have caught in the poll or you may not have, when we type intersection, we can't really type that symbol very easily. So what we'll do for intersection is we'll use a caret. It's the shift 6. It'll be intersect C. Same thing we might do to indicate an exponent. Here, clearly, we're not talking about an exponent. We're talking about intersection. And then for union, just capital U. Any questions on intersection or union? All right. Little bit of review of the words and or here. The difference mathematically is significant and important. The word and for us is going to go with intersection, because when we say intersection, we're looking for the elements that are in the first set and in the second set. This is where the sets overlap. And if an element's going to be in the intersection, then it must be in both sets. So all those words are kind of going to go together for us in set theory. And it goes with intersection. It's the overlap of the sets. And if you're in the intersection, you have to be in both of the sets. Or, it's a little different than that, or is associated with union. When we have union, we are going to join the sets together. And to be in the union of two sets, an element must be in at least one of the two sets. If you're in the first one, that's good enough. You're in. If you're in the second one, good enough. You're in. If you happen to be in both, no problem. You're in anyway. If you're in at least one of the two sets, you're in the union. Let me know if you have any question on that. A little bit of reminder of and or, how they relate to these and how they're different. Okay. Universal set and complement. First, we'll talk universal set. The universal set is all the elements that are under consideration. It's the entire universe. We started out with every number that exists as our universal set. We just didn't bring that up. But it's possible to sort of shrink what we're talking about by having a universal set. It might look something like this. Our universal set is 3, 4, 5, 6, 7, 8, 9. So once we know that that's our universal set, then no other numbers can exist for the rest of this problem that we're working on. That's our universal set. If you're thinking, how can I tell the difference between that being union and that being universal set? It's by context. If clearly here, this is U equals this, it's a set. So it's the universal set. If we want the union of two sets, we're not going to say that it's equal to something. It wouldn't go that way. We wouldn't say union equals. We would have to have A union B or C union A or something like that. So that's how we can tell that that's our universal set. So far, we're doing great today. I feel very confident with where your knowledge base is. This is the one idea that does sometimes cause a little challenge for student, and that's the complement of a set. The complement of a set is the elements that are outside of the set, but inside the universal set. So the complement of a set is everything that's outside the set, but inside the universal set. The way that we write complement, there's two ways you can see it in different books. You can see it as A with an apostrophe. That means A complement. Another way is A with a bar over it. That also means A complement. We're not going to use this one because we can't type it. We're going to use the one on the left there that has the apostrophe because we can type it. So our symbol for set A complement is going to look like this, A with the little apostrophe. And then just to sort of reinforce here the idea of the complement, A complement, that's everything that's outside of A, but inside the universal set. So I'm looking at A and it's 5, 6, 7, 8. I can see my universal set is 3, 4, 5, 6, 7, 8, 9. The complement of A is everything that is outside of the set, but inside the universal set. So my set is 5, 6, 7, 8. Outside of that, but in the universal set, then is going to be 3, 4, 6, 7, 8, 9. So A complement is going to be 3, 4, 9. Everything that's outside of the set, but inside the universal set, that's the complement. Let me know if you have any questions on what the complement is. And if you run into trouble with the complement later on, it's okay to ask then too. All right. Now we can put these things together. Intersection, union, and complement. We can put them all together and look at problems that involve those things. Here we're given 4 sets. We have our universal set is 0, 2, 4, 6, 8, 10. We have set A that is 2, 4, 6, 8. We have set B, 6, 8, 10. And we have set C, 2, 6, 8. And we're asked for 2 things down there at the bottom. We're going to do these together. It's perfectly fine with me if you want to try them on your own, but hang in there a minute. We'll do them together. The first one, very comfortable, very familiar. It's just A intersect B. Same thing we were doing before. We look up here at set A, we look here at set B, and we look for the intersection. That's where they overlap, what they have in common, the elements that are in both sets. And so A intersect B, let's see, that looks like it's 6, 8. Let me know if you don't see why that's 6, 8. If you think it might be something different, it's okay, we'll talk about it. If you're comfortable with the 6, 8, that's great. That's kind of where I expect, because we did so well with intersection before. Now at the bottom, we're asked for A union, B complement. Perfectly reasonable to think, am I supposed to find A union B and then the complement of that? Or am I supposed to find B complement first and then the union with A? And it's the second one. We're going to use parentheses to tell us what to do first and what to do after later on. For right now, this is just first find B complement, and then after you've done that, join it with set A. So the first thing we need to do is go over here and find B complement. And that's everything that's outside of B, but inside this universal set up here. All right, let's see. So it looks like that's 0, 2, 4, 6, 8, 10. Oh, that's it then. 0, 2, 4. That's B complement. Please let me know if you don't understand why that's B complement, or you think B complement should be something different. You want to discuss it at all. Complement can sometimes be challenging. I'd rather go ahead and address it while we're all here together. If we're good with B complement being 0, 2, 4, that's outstanding. Okay, now I have to answer this question that is A joined with B complement. I want to take A and I want to join it with B complement. That's what union tells me to do. So I'm going to take A over here. I'm going to join it with B complement over here. And when I do that, we have, let's see, 0, 2, 4, 6, 8. I've taken A and I've joined it with B complement. That's A union, B complement. If we're comfortable and confident in these 2 answers, that's outstanding. We're doing great. We've got some more practice to do, but as far as introducing new ideas, I feel like we're in a pretty good place. We're not quite done yet. We have one more new idea at the end, but let's do some practice. These are the same sets we had before. Our universal set is 0, 2, 4, 6, 8, 10. Set A is 2, 4, 6, 8. Set B, 6, 8, 10. Set C, 2, 6, 8. What I want you to do is find C complement, union B. I'll make a poll for it. Again, with these, it'll probably take me longer to type it than it does for you to come up with the answer. That's okay. Hang in there with me. So we're looking for C complement, union B. A good thing about these is they're very concrete. They're very here's what the numbers are. Find the union of those two sets. We'll probably go pretty quickly through these polls to make sure that I give you a chance to practice everything I want you to practice. So why don't we go another 20 seconds on this one, and then we'll talk through it. And I apologize for going quickly, but I want to make sure we see them all. All right, let's see how we did here. Okay, not unanimous, but strong agreement. That's very good. All right, so let's take a look at C complement union B. One little caution that I do want to give you is sometimes on a quiz, that apostrophe right there is not always that easy to spot. They're typed in there. You should be able to see them. Make sure you're kind of keeping an eye out for apostrophes that represent complement, because I don't want you to just not see one of those. Here, the first thing we're going to do is find C complement, and that's going to be everything that's outside of C that's inside the universal set. And so that looks like 0, let's see, 2, 4, 6, 8, 10. So C complement is 0, 4, 10. I did say I'm going to go relatively quickly through these, but if you have questions you want to ask, make sure you ask them. Now I want C complement union B. Union means join these together. So I'm going to join C complement that I just found over here with set B. And that'll be 0, 4, 6, 8, 10. And so C complement union B is that set right there. 0, 4, 6, 8, 10. All right, let's try another one. Same sets. Now we have parentheses involved. Parentheses do the same thing in set theory that they do in algebra. They say you have to do that first. So here, first, we're going to find A union C because of the parentheses. And then after that's done, then we're going to take the complement of that set. I'll make a poll for this, and I'll let you try it. The parentheses tell us you have to find the union first, then do the complement. We'll go another 30 seconds on this, and then we'll talk about it. If you happen to get one that's not listed, if you get an answer that's not shown there, pick the one that's closest to yours. That way I'll know you've had enough time. All right, let's see how it went. Okay, we have agreement, but we're spread around all 4 of those. If you have questions, please make sure you ask them. I get a sense that a lot of people are doing extremely well with this. That does not mean that everybody is. And so don't be shy if you have questions that you want to ask. It's perfectly fine. what you ask will probably help somebody in a future problem, even if they know how to do this one. All right, the first thing we're supposed to do here is find A union C. So I need to find A joined with C. So A union C is going to be, well, that's 2, 4, 6, 8. And all I did was join those two sets together. Anything in A, I kept it. Anything in C, I kept it. There's A union C. Now I want the complement of that. So what I want to do now is find the complement of this set. So that A union C complement is going to be everything that's in the universal set that's not in here. Everything outside A union C that's in the universal set. Let's see, that's going to be 0, 2, 4, 6, 8 are in there, and 10. And that's it. So A union C complement is just 0, 10. Let me know if you have questions on that one that didn't get addressed there when we talked through it. All right, some more practice. Here we're climbing up to the top of the mountain. Same 4 sets, A, B, universal set, A, B, C. This time, we have a problem that includes intersection, union, complement, and parentheses. It's all thrown in here. This one's got everything. The order we're going to do things in follows what you would expect. Parentheses tell us what to do first. Then we're going to take the complement of that, and then finally we're going to find the intersection with set A. I'll make a poll for this and let you try it. And that one at the bottom there is not a typo, it's the empty set. Remember, it is possible to get the empty set as an answer. I think this type of set theory where we're doing intersection union complement problems is really fun. They're like puzzles to solve. I think next week when we do Venn diagrams, that those are like puzzles to solve also, which in general, I find that to be kind of fun. I hope you do too. Students tend to do really well, especially with what we're doing this week and the intersection union complement ideas. But I do want you to ask questions whenever you have them. That's certainly in class today, but if you find yourself working on problems as you get ready to take quiz 3 and you want to ask questions, you can definitely do that by email or on the discussion board once we're outside of class time. Let's go another 20 seconds on this, and then we'll talk about it. All right, let's see how we did on this one. Strong agreement, getting strong agreement, but again, spread out across those answers. Wait, looks like it's showing the old one up there. That's interesting. Well, you can see it over in the chat, even if it's not showing up on that slide. So here, what the first thing we want to do is find B union C. That's the first thing we need is B joined with C. So we'll do that first. And that's going to be set B, which is 6, 8, 10, joined with C, which is 2, 6, 8. So that's going to be 2, 6, 8, 10. So that's B union C. That's our first step. Our next step is to take the complement of that. So we want the complement of that set. That's everything that's outside of here that's inside the universal set. So B union C complement is going to be, let's see, 0, 2, 4, 6, 8, 10. That's it, just 0, 4. That's going to be B union C complement. And then the last thing we need to do is find where does this intersect set A. So to end up with A intersect B union C complement, let's see, where does set A intersect B union C complement? The only thing they have in common is that 4. And so our answer is just a set with 4 in it. That's it. A intersect B union C complement is the set with 4 in it. Let me know if you have questions on that. We have one more new idea. That one more new idea is cardinality. And the number of elements within a set is known as the cardinality of that set. Cardinality means the number of elements that are in a set. We kind of saw this earlier when we talked about equivalent sets. Two sets are equivalent if they have the same cardinality, if they have the same number of elements. The way that you know that a question is asking you for cardinality is you'll see a little n in front of the parentheses. That means we're finding the number of elements that are in this set. Be on the lookout for that little lowercase n when you take your quiz, because when we're asked for A intersect B, we just list it out in roster form. But when we're asked for lowercase n of A intersect B, all that's asking us for is the cardinality. What is the number of elements in that set? Now, to answer that question, the first thing we'll do is we'll go find A intersect B, and that is, let's see, A is 5, 6, 7, 8, B is 6, 7. So A intersect B would be 6, 7. The way that I answer this question, though, is I say, well, the number of elements in that set is 2. And it's just a number answer, and that's it. I really like these questions for quizzes and for exams because, as Laura mentioned earlier, typing something in roster form can be a little clunky. So I like asking cardinality because then you just have to type a 2. Maybe you had the wrong 2, but I don't think so. I think if you get the cardinality right, chances are you had the correct set. Down here, the cardinality of C complement. Well, C complement is everything that's outside of C but inside the universal set, and that's going to be 4, let's see, 5, 6, 8, 9. So the cardinality of set C, or excuse me, C complement is 4, because that's how many elements are in C complement. Be on the lookout for those little n's, because that tells you you're looking for cardinality, and I like asking that because it's easier for you to type. Not all the time, but definitely some of the time. I'll ask you for the cardinality